Hello everyone. So in this video we will see the conflicts that occur in instruction pipeline. In previous video we have seen the arithmetic pipeline and instruction pipeline. So in this video now we will concentrate on instruction pipeline conflicts. So it caused the instruction pipeline to deviate from its normal operation. So normally it goes one by one phrase by one phrase, right? Whenever there is some conflict, it deviates from its normal flow. So which are the different conflicts that are possible? The first is resource conflict, second is data dependency, and third is branch difficulties. So these are the three different instruction pipeline conflicts that deviate the flow of instruction pipeline. So resource conflicts. So it caused by the access to memory by two segments at the same time. So suppose fetch instruction, it is also accessing the memory to get the instruction, and fetch operand, that phase also accessing the memory to get the operand. So this is conflict, right? So either one segment will get the access to memory. So most of these conflicts can be resolved by using separate instruction and data memories, right? You can have different memories for instruction and different memory to have store your data, and you can have a different bus as well, right? For instruction you can take from another, and for data you can take your data from another bus, right? So this can be resolved like this: resource conflicts. Data dependency. So conflict arise when an instruction depends on the result of previous instruction, but this result is not yet available. So one instruction is waiting for the output from the previous instruction, right? As the output is not available, that instruction cannot process. So that is called a data dependency, right? We will solve how to solve this data dependency in next videos. Branch difficulties. So it arises from the branch and other instructions that are changes the value of program counter. So whenever there is a change in program counter, the normal flow will be deviated, right? So that is a branch difficulties. So let's see how to solve this data dependency, as we have already seen how to solve this resource conflict, right? So data dependency, it occurs when instruction needs data that are not yet available, right? As one instruction executing, after that we will get the result, right? But the data is not available in the next instruction, right? So that instruction need to wait. An instruction in fetch operand segment may need to fetch an operand that is being generated at the same time by the previous instruction in segment execute, right? So execute, after this we will get the data in fetch operand, right? So that instruction need to wait, therefore the second instruction must wait. So address dependency may occur when operand address cannot be calculated. So that is address dependency. So solution to data dependency. What is the solution? First is hardware interlocks. So what is that? So interlock is a circuit that detects the instruction whose source operands are destination of instruction farther up in pipeline, right? So it detects, right, that this instruction result will need by some another instruction. So instruction whose source is not available to be delayed by enough clock cycle to resolve the conflicts. So we know that the second instruction will not get data unless the first instruction completes its task or execute phase. So that instruction will be delayed by some clock pulse, right? At that time you can execute another instruction, or your CPU will execute another instruction, right? So this can be solved. This is one solution for your data dependency. The second is operand forwarding. So it detects a conflict and then avoid it by routing the data through special paths between pipeline segments. So after performing the operation, that result is going to be stored in some register file or something. But before doing that, we can immediately pass this result to the instruction which is waiting for this, right? So that is called a operand forwarding. We are bypassing the storing and we are directly giving the data to the instruction. So instead of transferring ALU result into destination register, the hardware checks the destination operand, and if it is needed as a source in the next instruction, it passes the result directly into ALU input, bypassing the result register file, right? So this is operand forwarding. Next is delayed load. So the compiler for such computers is designed to detect a data conflict. The compiler will detect the data conflict and it reorder the instruction as necessary to delay the loading of conflicting data by inserting no operation instruction. So your compiler will perform this task, right? While your compiler is generating your machine level code, at that time compiler will detect such instruction and it insert the no operation instruction at that place. So when your instruction execute, at that time that instruction gets the data, right? So that is the delayed load. We are delaying the loading of the operands. Next is branch conflicts, difficulties, right? So resource conflicts, the second is data dependency, and third is branch difficulties. So how to resolve these branch difficulties? So branch instruction can be conditional or unconditional. So in conditional branch, based on some value, it may go sequentially or it may jump to somewhere else. In unconditional branch, it will not check any value, it will directly jump, right? In both the cases, it will affect your pipeline, or you can say normal execution. So it breaks the normal sequence of instruction stream and causing difficulties in the operation of instruction pipeline. So how to handle this branch instruction? So first is prefetch target instruction. So prefetch the target instruction in addition to the instruction following the branch, and both are saved until the branch is executed. So we are not only storing the next instruction, but we are also fetching the target instruction. If this condition goes, okay, then what will be the target instruction? So that also we are storing. Then branch target buffer, BTB. So this is associative memory included in the fetch segment. This is the associative memory and it is included into fetch segment. And each entry in BTB consists of the address of a previously executed branch instruction and the target instruction for that branch. So it will store this address of previously executed branch instruction and the target instruction both, right? So why? So in future, if such kind of instruction will execute, then in BTB we have a data, so we can directly put that instruction, right? We can directly access that data or we can directly access the target instruction. It also stores the next few instructions after the branch target instruction. So in this we are just storing the target instruction, but BTB it will not just store the target instruction, but it will store the few instruction after the target instruction, right? So you will easily get those instructions. Third is loop buffer. So it's a variation of BTB only, and it is small and very high speed register file. So what it will do? So when a program loop is detected in the program, it is stored in the loop buffer in its entirety. So it will store that loop including all branches and then it will execute that. Okay, so the loop mode is removed after the final branching out. So once all the branching is done, then the loop will be out. Fourth one is branch prediction. So these are the solutions that we are uh, right now seeing. Branch prediction. Use some additional logic to guess the outcome of a conditional branch instruction before it is executed. So in previous cases, we were storing for sequential approach and target instruction both. But here it will guess the probability, that what is the probability of sequential or what is the probability of jumping to the target instruction. So based on that, it will select any one and then it will move further. So the pipeline then begins prefetching the instruction stream from the predicted path. Suppose it predicted that this condition, if there is a jump, then it will move to the condition, that is a 90% chance. So what it will do, so after that instruction it will start fetching those target instruction and instruction after that target instruction, right? A correct prediction, it eliminates the wastage of time caused by the branch penalties. So if our prediction is correct, then we have removed the, or we have stopped this time wasting, right? So and if in remaining 10%, if this goes wrong, then there is branch penalties, right? The fifth is delayed branch. So it employed in most of the RISC processor. A compiler detects the branch instruction and rearrange the machine level language code sequence by inserting useful instruction that keep the pipeline operating without interruptions, right? So compiler detects the branch instruction and it will rearrange your instruction, right? So you will not get much, your pipeline not get much affected by this. Okay, so these are the different possible solutions that we have seen for data dependency and for branch difficulties. Thank you.